In today's video, we shall take a closer look at the concepts behind angular momentum. We know that if you have an object whose mass is m and which moves with a velocity v, this object has a linear momentum given by the product of mass and the velocity. So this is what we call the linear momentum. Now let's assume the same object is moving along this curve, like that. At that point, it has a linear velocity v, and the position vector of that particle is given by this vector r. And this position vector is defined with respect to that origin. If the mass of the particle is m, now we can define the so-called angular momentum of this particle with mass m about that origin, and the expression is given by the following. It is the mass times the cross product of that position vector and that linear velocity. So this angular momentum is defined with respect to that origin. You can see as the particle moves, the position vector can be viewed as rotating about the origin itself. Let's apply the same concept for a particle that is moving in a circular trajectory, and the axis of rotation is going through the middle of that circle and coming out of the board. The linear velocity is v, or the tangential velocity is v. Position vector is given by that, let's assume it's r, and the mass of the particle is m. So in this case, the angular momentum of this particle about that axis of rotation is mr cross v. The magnitude of that position vector is simply the radius of that circular trajectory. Now you can see, since the angle between that position vector and the tangential velocity is 90 degrees, the angular momentum magnitude can be written as quite simply m or v. Because the object is moving in a circular trajectory, counterclockwise direction, of course we can assign the angular velocity to it, and the angular velocity is given as the tangential velocity over the radius of that circular trajectory. So substituting that in here, you get mr squared omega, which brings an important point. The product of mr squared for such a point particle is quite simply the moment of inertia of that point particle with respect to that axis of rotation. So we can write the angular momentum as the product of moment of inertia and angular velocity. In vector notation, it looks like that. The first expression can be applied specifically to a single particle, whereas the second expression is true in general, meaning it can also be used to define the angular momentum of rigid bodies or solid bodies. Let's quickly look at an example. Assume that you have a mass 0.5 kg with position vector r given as -3i hat plus 5j hat, defined with respect to some origin, with some velocity v defined as -5i hat. So the unit is of course meter per second. The unit for position vector is of course meter. What is the angular momentum of this particle with respect to that origin? Well, it is given by the formula that we have just derived. So mass in this case is 0.5. Now this is a cross product which can be evaluated in determinant form, I hat, j hat, k hat. The first vector is the position vector, so -3, 5, and 0, because it doesn't have any k hat component. The second vector is the velocity vector, -5, 0, 0. And when you compute this cross product, and don't forget to multiply by 0.5, you get the angular momentum to be 12.5 k hat. The unit is of course kg, meters squared per second. So this is how we compute angular momentum of a point particle with respect to a given origin. Now let's look at the following example. You have a disk that is spinning about this axis, passing through the middle and coming out of the board. Let's assume that the angular speed is 2 radian per second. Let's assume the mass of this disk is half kg and the radius is 1 meter. So what is the angular momentum of this disk about that axis of rotation? It is the product of the moment of inertia and angular speed. The moment of inertia for such a disk is given by half times the mass times the square of the radius times omega, which is the angular speed. Putting in the numbers, you get half, the mass is half kg, radius is 1 meter, so 1 squared, and omega is 2. So the answer is half kg meters squared per second for the angular momentum. Now what about the direction of this angular momentum? The direction of the angular momentum is the same as the direction of angular velocity. Now because the rotation is counterclockwise, from our previous video, using the right-hand rule, we know the direction of that angular velocity is coming out of the board. So the direction of angular momentum is also coming out of the board. Now let's express Newton's second law in terms of angular momentum. This is Newton's second law for rotation. We know that net torque can be written as the product of moment of inertia and angular acceleration. And since we know the angular acceleration is given as the time rate of change of angular velocity, putting this in here, you get I times d omega dt. Assuming I is constant, we can take the I into the derivative sign and write it like that, which in turn gives us d dt L. What that means is net torque is given by the time rate of change of angular momentum. This is Newton's second law for rotation in terms of angular momentum. Now let's see what is the implication of the net torque acting on the system being 0. If that is the case, then we know the time rate of change of angular momentum of the system has got to be 0. That means the angular momentum of the system has got to be a constant vector. So this is the expression for conservation of angular momentum, just like the conservation of linear momentum. What that means is when there is no net torque acting on the system, the angular momentum of the system is conserved, which means the initial angular momentum of the system must be the same as the final angular momentum of the system. So let's see how to apply conservation of angular momentum to problems. Here, 2 kg balls are attached to the ends of a thin rod of length 40 cm and negligible mass. So one ball is here, another ball is there, and they are connected by a thin rod, like that. The rod is free to rotate in a vertical plane without friction about a horizontal axis through center. So that means the axis of rotation is like this, and the system can rotate like that, or like that. With the rod initially horizontal, a 45-gram tiny object drops on one of the balls, hitting it with a speed of 3 meters per second. So assume that that's the tiny object and it's hitting the right-hand side ball with a speed of 3 meters per second. After the impact, the tiny ball sticks to that ball. Find the angular speed of the system just after the tiny object hits. So what you have here is the initial state. Now the final state is when the impact already happens. So that is the rod system, and the tiny object now sticks with it, and this entire system starts to move like that with some angular speed omega, and that is what we want to find. And the rotation is again about the center. Assuming there is no net torque acting on the system, the initial angular momentum must be the same as the final angular momentum. So we are using conservation of angular momentum to solve this problem. Let's calculate the initial angular momentum. The initial angular momentum is due to only that tiny object, because this ball and that ball, this entire system that is, were not moving. We are going to treat this tiny ball as a point particle, and we know the expression for the angular momentum for such a tiny particle, the mass of it times the distance from the axis of rotation, r, times v, which is that tangential speed. The mass of that tiny ball is 45 grams, so it's 45, turn that into kg, divide that by 1,000. The length of this entire rod is 40 cm, so that means r is half of that, is 20 cm, turn that into meter, 0.2, and the speed before the impact is 3 meters per second, so times 3. Now let's determine the final angular momentum of the system. This entire system is moving, so the left-hand side mass will start to move upward like that. The right-hand side mass will move downward, together with that tiny object will also move in a downward direction, all with an angular speed of omega, or linear speed of v, which is given by r times omega, r being that distance, 20 centimeters. So let's model all these objects as point particles. Let's start with the one that is on the left. The mass of that is 2 kg, that's given. The radius is 20 cm, so 0.2 meter. And the speed is v, given by r times omega. R is again 0.2, so you can simply write it as 0.2 squared times omega. Now let's do the right-hand side contribution. The right-hand side of that blue ball, that would also contribute the same amount because its mass is 2 kg. The distance from this axis of rotation is 20 cm or 0.2 meter, and it has the same speed, and therefore the angular speed omega, which is given by 0.2 omega. So 0.2 times 0.2, 0.2 squared omega. So that is the second contribution. And finally, the contribution from the third object, which is that tiny object. Its mass is 45 grams, so 45 over 1,000 to convert that into kg. The distance from the axis of rotation is 20 cm or 0.2 meter. Its speed, v, is given by r omega. So this omega is there, and this r is 0.2. So times with the existing 0.2 will give you 0.2 squared. So conservation of angular momentum states this must be the same as that. So we equate the two and solve for the only unknown, which is omega. And when you do that, you get the following answer for omega, which is 0.167 radian per second. And that solves the problem. As always, thank you for watching.